using only 2-butanone and ethyl 2-bromoacetate, develop a synthetic sequence for the formation of this product here, this alpha-beta unsaturated ester. So before we determine what kind of reactions we need to use, let's just count the carbons. In 2-butanone, we obviously have just 4 carbons, and in ethyl 2-bromoacetate, we have only 2 carbons. But the product here has 4 carbons, so we can't just simply stitch together these 2 compounds to form this alpha-beta unsaturated ester. So in some way we need to reduce the carbon count here and then form a carbon-carbon bond, most likely a double bond, which is E in nature, trans, and also yields a product with only 4 carbons. So how do we do that? One of the goals for the synthesis is to reduce the carbon count by 2. And this has to occur with 2-butanone. We then need to add our alkyl halide, which is essentially what ethyl 2-bromoacetate is. And if we add our alkyl halide to this modified ketone, we could form this compound here. So let's add alkyl halide and form the product, which must have the alkene. That's a requirement. Now the key reaction here, which helps us break up this ketone, is the Baeyer-Villiger reaction. So to start, we take our ketone and we carry out the Baeyer-Villiger, where we need MCPBA and some kind of polar aprotic solvent, dichloromethane. And what happens is MCPBA inserts an oxygen atom on the more highly substituted side of the ketone. So here we have an asymmetric ketone. On this side it's primary, but here it's secondary. So we can take 2-butanone and form ethyl acetate using MCPBA. And in the process we formed an ester which can then be hydrolyzed. So that's what step 2 is. Now this is an ester hydrolysis reaction, which is acid catalyzed. This portion of the molecule is coming from this part of the ester right here. And this ethoxy portion of the molecule is what forms ethanol. So we can hydrolyze this ester such that we form 2 different components that are 2 carbons each. And now that's our gateway for the next step. So we've already reduced the carbon by 2. Now we can add the alkyl halide and form a product that has an alkene. But we need to keep in mind that it needs to be in the trans configuration. So now what we need to do is take acetic acid and form a carbonyl, because the carbonyl is our versatile substrate for an alkene forming reaction, which is accomplished by the Wittig reaction. What we can do with the Wittig reaction is take a carbonyl and an alkyl halide and form an alkene with a specific stereochemical designation. So in this case, the alkyl halide is bromoethyl acetate. And if we analyze our alkyl halide at this carbon right here, we have an adjacent pi bond. So in theory, if there were ever to be a lone pair that's hovering around this carbon, it can be conjugated with the carbonyl that's part of the ester. So if we have a stable ylide in the Wittig reaction, we can form this stable alkene. So let's try to form a 2-carbon carbonyl compound, and that's by using acetic acid. So let's take acetic acid and transform it into our Wittig substrate. One way is to react it with a mild reducing agent. So if we use lithium aluminum hydride, we don't form the carbonyl. But if we use a modified hydride reducing agent, such as dibol, we can form the carbonyl. Now dibol must operate in an aprotic environment at very low temperatures, and in the second step we quench it with aqueous hydrochloric acid as the workup. So that's how we formed the carbonyl. So we formed our Wittig component number 1. Now let's bring in the second component and react them together. So here is ethyl bromoacetate, which needs to be refluxed with triphenylphosphine in toluene. And in the second step, we can bring in our carbonyl, and we can call that compound 1. We also need a strong base like N-butyllithium to form our ylide. And just like in the first step, we need an aprotic solvent, and THF works just fine. So the result of this reaction is we form our alkene, our transalkene, because this is a stable ylide. Let's try to number our carbons. There's carbon 1 and there is carbon 2, and we can bring in those pieces right here. And instead of the carbon-oxygen double bond, we have a carbon-carbon double bond, where the carbon would be right here. That is where the alkyl halide comes in. So this is carbon 3, and this is 4. And we can add in those carbons as well. So here's 3, and here's 4. And just to finish the structure, at carbon 4 we have a carbonyl. And then coming off of carbon 4 we have the ethoxy group, which is also attached right here.